Laura, can you please remember how much time I have?
Let's say 25 minutes and then 5 minutes for questions.
Okay.
And the same holds for everyone.
Mm-hmm.
2 minutes.
Should we start sharp or have the...
I think it's better to start sharp because then you will not be sharp talking. It's so very easy to add some delay.
Yeah.
And there are different channels, so people would like to move from one channel to the other.
Yeah.
It's possible. Massimiliano disappeared and left his name. You are back. You are moving.
Yeah, I need a coffee, and I wanted to spare you to to visit the house.
So, typical British house.
Yes, and also typical British weather so far.
Here we have air conditioning. Okay, I think we can start our mini symposium. Thanks to all the participants. Somehow the title is mixed because we have both statistical and modeling problems in the study of spike strains, and we will range from more mathematical aspects with the first talk to statistical and modeling parts with the following ones. So our first speaker is Bruno Aldo from my university, the Torino University, and he will talk about a semi-Markov integrated end-fire model for neuronal activity. Please, Bruno, we can start.
Okay, can you hear me?
Yes, we do.
Very well. You are probably seeing my slide now?
Yes, we
Very
do.
well. Okay, so the difficult part is done. Okay,
yes.
So thank you. Thank you to all of you for being here, and thank you to the organizer for giving me the possibility of explaining you something of my work. So my name is Bruno Aldo. I am in principle a mathematician, but I recently enjoyed the possibility to apply some of the things I am studying from the mathematical point of view to this exciting field, which is neuronal modeling. Okay, so it is thanks to Laura and my co-authors, Giacomo Ascione and Enrica Pierozzi, that I started to believe in this application. The point is, what I work on is consonant with first passes time of random processes, and therefore this probably remind you the possibility to study and to use first passes time of random processes in the context of leaky integrated and fire model. Okay, so this is a very very easy approach to the mathematical modeling in neuroscience. So the idea, the very basic idea, which you certainly know better than me, is to have is to describe the membrane potential of an neuron with some random process. For example, a random process which is a strong solution of an SDE, which is written here on the slide. If you see the arrow of my mouse, probably I can highlight something for you. Because these quantities can have a nice interpretation in this context. So one has that capital VL is the leak potential, theta, the parameter theta is the characteristic time in the RC circuit. And then the leaky part is a locally integrable function which represents the stimuli, the input stimuli. And the random part, so what makes it random is this noise, which is a white noise, and thus W is just a Brownian motion, so a linear process. One says that a neuron fires if it emits the signal when the random process capital V cross a fixed or eventually moving boundary, which is capital V of t. Then there are different approaches to what happened later. One can reset and let's start the mechanism from the beginning, or you can move the threshold. So there are different approaches later. But we focus in this talk only on the first part, and then the classical approach are applicable to what I'm saying now. So it is clear that in this framework, the distribution of these random variables, so the first time the process crossed the threshold is crucial. And the very historical paper on this started to consider this quantity in 1962, where in some seminal papers by Gerstein, they took, they plotted some neuronal, this quantity, okay? So they plot the histogram of this random variable for after observing some neural units in the cochlear nucleus of the cat. And the authors realized that, in particular, one of these units, which was considered representative, is this histogram is unimodal asymmetric, and clearly its decays was not an exponential. So this means that in order to fit data, one model based on this quantity should be a random process whose first passes time to some threshold as a slow decay, okay? So which is not exponential. And there are several attempts have been made, and there are several approaches in the literature to fit this and this this decay. And some are essentially based on the exponential function, which is in principle apparently not correct. Other on gamma distribution, which is still an object whose decay is exponential. But the most commonly approach is given by the author of the first paper itself, which is Gerstein and Mandelbrot, which is a very historical paper in this topic. And they essentially believe that this decay can be fitted with a stable law. So with power law decay of the distribution, which in principle could be parameterized, okay? Because if it is a power law decay, so a stable law with alpha stable parameter, you can in principle estimate the parameter alpha. So it turns out that in the very classical model described above, the solution to the SDE is a slight modification of an Austin-Uhlenbeck process. So in this case, it can be proved that the intervals between spikes, so fires in the neuron, have an exponential trend. The question is if it is possible to obtain a linear model having a very easy model like this, having the same interpretation of the parameters, such that the trend can be fitted to be not exponential. The trend of the distribution, so the tail of the distribution, the fastest time, can be fitted to be not exponential, but some heavy tail distribution with some parameter that you can tune. And the point is that this is my question, but actually most of the literature concerning in more recent years, not related to 1960s, essentially relies on the use of Markov processes. But with Markov processes, the point is that it is very hard to build, in the sense that I've not been able, and as far as I know, it is not easy, it is not possible to get this clear heavy tail behavior for the first passer's time in having a parameter. Okay, of course you can have, it is easy to use some Markov processes whose distribution of first passer's time is heavy tail, but it will be not related with the SDE above, and it can be, and you will not have a parameter to tune the curve, to tune the decay. So essentially the reason of the use of Markov processes, my feeling is that the use of Markov processes is therefore due to the easy mathematical approach that can be used to deal with the first passer's time problem. Okay, so if you have a Markov process on some filtered probability space, and you take the exit time of this guy from any set, then this quantity, if you put capital G to be the open interval minus infinity C, then this is the first passer's time to a threshold. Okay, in general, this is a stopping time, and as you can use the theory of stopping time for Markov processes. And so in what follows, I will use the classical notation from Markov processes. Okay, so when you see capital PX and capital EX, it means that we are conditioning the process to start from here. And with the symbol P capital TX, we just mean the density of the passage time of Markov process. So I was saying Markov processes have a lot of comfortable properties in the sense of exit times, not only for modeling. And for example, you can estimate the first passage time distribution in very explicit form in some cases. For example, if you have a Brownian motion, you can have an explicit density, even if the Brownian motion is with drift, then you have a closed form for the density of the first passage time. And in the case above, so for example, if you take an Osten-Uhlenbeck process, which is just a bit easier, but it holds also in the more general case, so in the leaky integrated fire case, the exit time from minus infinity C, so the first passage time to level C of this process, is asymptotically behaves to infinity like an exponential. Okay, so we are still in the exponential case. This is not an explicit representation. So this is an asymptotic behavior. But okay, who cares? If it fits data far from zero and close to zero, then one has that more or less the distribution is this way. In general, if you take and Markov processes, a Markov process associated with an SDE, so processes having this form are continuous, have continuous path. In general, you have that they solve the survival function conditionally to the point X satisfy a PDE. Okay, so this is another reason for which the theory of first passage time of Markov processes is easily to be applicable in this context, because you can essentially solve a PDE numerically if you want to have precise information on this distribution, even if you cannot compute this precisely, explicitly, or you cannot estimate. You know that it satisfies a PDE. So from this PDE, you can get a numerical solution. So you can, in applications for mathematical modeling, approximate this quantity effectively. And the letter A, capital A here is the generator. Okay, so this is something you can obtain starting from the governing SDE. So the idea, our idea is to introduce a model which is very, very close as in the sense of interpretation to the original leaky integrated fire model. But we introduce a random time change of the model, of the original model, which essentially means that we are making the evolution, the original evolution, faster or slower. Okay, so we are introducing something which makes things faster or slower randomly. Okay, of course, this guy here is not an arbitrary process, but what I will tell you now is how to construct this process. So how to choose this capital L. and the possibility that you will have in order to fit your data. This is the idea. So in this case, one has that the solution to this process, to this equation, sorry, is the solution capital V to the original equation, so with no time change, with the random process, capital LT. And this can be stated rigorously, okay? So I didn't put here the rigorous statement, but there is a paper, there are a couple of papers on this. So this is a well-posed SDE with strong solution, and everything works well. And what it turns out is that this process here, so the time-changed process is not Markovian, but semi-Markovian. And what does this mean? And what is the distribution of the first exit time are the questions I want to answer now. So, what is a semi-Markov process? You know, when you work with Markov processes, in particular in the context of neuronal modeling with continuous processes, so look at the second path. You know that a Markov process, which is in our case is something like an Austin-Uhlenbeck, but in any Markov process can never stay constant and leave the point continuously. Okay, so if a Markov process stays constant, then it must stay constant for an exponentially distributed time, and then it must jump away. So it cannot leave a point where it is continuously. If it leaves a point continuously, like Brownian motion, then it is never constant. Okay, so there are no other possibilities. Semi-Markov processes allow this possibility. So essentially, heuristically, the idea is that you can take the class of Markov processes and add these two features, and then you get the class of semi-Markov processes. But of course, when you introduce this possibility, what happens is that imagine that you know all the paths of a process up to a certain time s. So at this time, you know everything about the process, and you want to compute the probability of something in the future. Then the quantity gamma of s, which you are ignoring in the Markov case because of the lack of memory of the exponential distribution, becomes relevant. Becomes relevant because, of course, you don't have exponential time, and thus you are conditioning an exponential random variable to be greater than something, and this is relevant when the waiting time is not an exponential. When it is an exponential, like in the Markov case, you can avoid to consider this. And thus one possibility to define a semi-Markov process is to say that it is Markov together with this coordinate. So if you keep this information together with you and you introduce this quantity gamma of t, then what happens is that the couple here is Markovian. So one says that X is semi-Markov, this is Markov. This is one possibility to define the class of Markov processes. So when you compute probability in the future of some point S, you must keep it with you. So this gamma of S is relevant. So the time change construction, as introduced in the SDE above, can be explained by resorting to a new process, another external process which is called sigma. Okay, so actually this coordinate here is the most important one, even if we time change with capital L. So in the SDE above, the key quantity is capital L. But it turns out that this capital L is the inverse of another process. So it is easier to introduce the other process and then having the other process, you get your random time. So the external process here is sigma. Imagine that we want to time change capital L. We have a process here which is called sigma, which is increasing and jumping. And when you take the first passage time of this guy here through level t, so it's inverse, the jumps of this coordinate becomes intervals of constancy. And thus, if you use this capital L to time change capital N, which is another arbitrary Markov process, what you get is something which remains constant between the point in the range of this external process sigma. So essentially, we are constructing a process which is continuous because this guy here is increasing, and thus capital L is continuous. And it has the value of a Markov process, which is kept on a random time. And the random time is determined by the jumps of this object here, this process sigma. So essentially, we are constructing a process which leaves point where it is constant continuously. Okay, so we are taking a Markov process and we are randomly stretching its path. So we are introducing a delay randomly chosen, in the evolution of the Markov process. So in order to introduce this more rigorously, be patient. This is a couple of slides of math. I need to introduce the concept of Bernstein function, which is essentially functions which are non-negative, non-convex, and whose derivative is completely monotone. But what is important is that a function, to be a Bernstein function, must be represented in these ways, and vice versa. So this is the class of Bernstein function is in one-to-one correspondence with the class of functions having this representation. And so given A, B, and a measure, you have one Bernstein function, and any Bernstein function is associated to one process sigma, which is the one we are interested in. But later we will always work with this guy here, A and B 0, so you can forget about the meaning of this quantity and just recall that this quantity here, this measure here, will be considered as an infinite measure, so that this integral is convergent, and it is related with the height of the jump of the process sigma. Okay, so the height of the jump of sigma and thus the length of the interval of constancy here. So we take capital L, the inverse of this process sigma, which is related with the Bernstein function above, being the Bernstein function is Laplace exponent. Okay, so this is the reason why I introduced the Bernstein function. And under, of course, given any Bernstein function, there is a process sigma, which is called the subordinator. And given any subordinator, then there is a Bernstein function such that the equality is true. And under our assumption, we will always have that this process sigma is strictly increasing if pure jumping. So the inverse is continuous and non-decreasing, and it is an absolutely continuous random variable for any fixed t. So if you take a process, a Markov process here, like the one we used in Leaky integrated Fire model, and then we time change with this capital L, then we suppose independence on the true process. What we get is that this time changed process, which is the solution when we choose X to be capital V, so often in the bed, to the SDEs introduced above, then this process here is semi-Markov, is a semi-Markov process, okay, exactly as above. And what we did concerning this process is to give an approximation. So we estimated the distribution of the first passage time to a constant ratio. So the result here looks to be difficult understanding. But let me start from the easy case. The easy case is this one. So suppose that the process before as a first passage time to a threshold, which is with finite expectation, okay, like in the Austin-Uhlenbeck case. And then we perform the time change, and this function here represents the time change. Okay, choosing this function here, we are essentially choosing the process which introduced the delay or the random time change in the evolution. Then this new process has a first passage time, the time changed process has a first passage time, which is this calligraphic T, whose tail behavior is determined uniquely by the function phi. So the process we are using to introduce the delay. So essentially deciding which is the random time change, we are deciding what is the decay at infinity of the survival function of the first passage time. Then the original process affects the tail behavior, in this case, only with the constant in front of it, which is the original expectation, which is a number, okay, a parameter. In the case of Austin-Uhlenbeck, then here there is theta, so the quantity appearing in the SDE in the RC circuit. The general statement is just more general about this, but of course, if the expectation of the original Markov process is not finite, then it affects the behavior of the waiting times even later, even after the time change, and so the behavior at this form, and G is the behavior it's the behavior of this function here. Okay, so it is determined by the original time chain, by the original Markov process. Sorry. So some examples. In Brownian case, we have this. So if we are time changing the Brownian motion, we have this for any boundary. See, if the Brownian motion starts, sorry, this is Brownian motion with drift. If the Brownian motion with drift start at 0, then we have this behavior of the survival function. For a standard Brownian motion, which has infinite expectation before the time change, then the behavior after the time change is given by this quantity. And here appears the effect of the delay. So the function phi is here. For the time change of the Austin-Uhlenbeck process, so time change of the classical leaky integrating file model, what we get is by making this choice of time change, so introducing this parameterization, is that the tail function of the first passes time through a fixed threshold have this nice behavior, which is exactly a power law for alpha in 0, 1, and C is a parameter which depends on theta, the original parameter theta, and so you can essentially to make these things fit data, you can just tune alpha and you can tune the parameter C of theta, and you have exactly a tail behavior, exactly the tail behavior suggested by Gersten and Mandelbrot, and you have a model which essentially the same interpretation, okay, because it is just a reparameterization. And the reparameterization is due to the time change, the random time change. What we did is then to estimate also the behavior at 0, and to estimate the behavior at 0 in order to check that what happens to the time change, to the distribution after the time change close to 0, not only when t is to infinity. So we estimated this quantity at 0, okay, the distribution of the first pass time through a level when t is close to 0. And this is again, as above, maybe hard to understand, but this is a bit easier. What happens in this case is that if the original behavior before the time change, so before the delaying, this quantity here goes to 0 faster than any power, then it still do this faster than any power after the time change. Okay, so this is what it is needed in the context of the time change of the Austin-Uhlenbeck process. This is just the general statement. Okay, so if you have the behavior at the before the time change is this behavior with this capital F function, then after the time change, the time change is affected by introducing this rescaling here. Okay, so I told you before, the last thing, and then I finish. I told you before that Markov processes were suitable and were comfortable, because if you don't have information on the first pass time distribution, then you could solve a PDE numerically. Okay, so you can write a PDE using a generator. Then you can always find an approximation about this, about the distribution of the survival function, okay, because it satisfies a PDE. And what we believe it is true, and we have something more data conjecture, even if this result is not published, is that this is true also in this case. But the PDE is not local. The PDE is given by is given by this form here, and it is non-local in the time variable, in the sense that there is an integral differential operator appearing on the left-hand side. But this guy here is not hard to be dealt with numerically. Okay, so this is something which is still not proved. But what we, okay, there is a mistake here. It is bigger than, not less or equal to, sorry. So the survival function satisfies this object here. And so also in this case, if you are working with a time-changed process and you don't have, and you want some precise information about the tail behavior or about the distribution for fixed t and x, you can still use the numerical approximation approach of PDEs.
Bruno, it's time.
Yes, okay, I finished. Thank you for your attention.
Thank you. Thank you, Bruno. And we have really a few minutes for questions. Does anyone has a question? You can type in the chat and I will read, or you can switch your microphone if you are connected using Zoom. No comments. I wanted to only underline that you spoke about heavy tails, saying that Markov models do not exhibit heavy tails, and you are right if you think to a constant boundary, but if you think to time-dependent boundaries, you can get heavy tails.
Yeah, sure. Yes.
It's a different perspective.
I also agree with this assertion when the boundary is constant, but what it is difficult to me is to find a parameterization. So as far as I know, you should find a family of Markov processes with a tail behavior which is power law, whose decay alpha is the same parameter of the family of Markov processes. This is something which is hard which I am not able to find. Maybe with your approach, you could introduce the parameter in the boundary, and then you have parameterization of the boundary, which induce a parameter alpha in the decay. This is possible. Yes, maybe, but we are not saying just that Markov process cannot have a key tail in the passage time. Yes, of course it can, but with which parameter? Like, can you parameterize the decay?
No, you are right.
Something I'm not sure is possible.
I agree. Yes, you're right. In this sense, I understand. Any further comment or questions? No. Otherwise, we thank Bruno again.
Thank you.
And we switch to the next speaker. She is Alessandra Stella from Jülich Forschungszentrum. And now we switch really from math to a statistical problem. And she will speak about surrogate techniques for testing higher order correlations in parallel spike trains. Please, Alessandra.
Thank you. Can you see the slides and can you hear me well?
Yes, we do.
Okay, thank you. I just moved the Zoom panel. Perfect. So thank you, Laura, for introducing me. Thank you for inviting me. Yes, I work at Jülich Forschungszentrum at the Institute of Neuroscience and Medicine in Germany. And this is joint work done together with Peter Booth, which is another PhD colleague of mine, Professor Gunther Palm and Professor Sonja Grun. So the title is already quite clear. The context is pretty much different from the previous talk. But I hope that it will be anyways interesting for you. What I'm going to present is starting from the context. The background is the Hebbian assembly hypothesis. So Donald Hebb theorized in 1949 that assemblies of coactive neurons act as information processing units. With Hebbian assemblies, we are talking about groups of neurons that are co-activated time after time and in different space within the brain. This is theorized. There are already some experimental evidences, but context and different backgrounds can be very, 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 very different. So our more precise hypothesis is that the assembly membership is expressed by precise temporal coordination activity in the range of a few milliseconds. So typically speaking, this is what also is called in different words as temporal coding. This is not an easy hypothesis. Actually, it is pretty much different and complicated to test it statistically. There are different approaches to test higher order correlations or pairwise correlations in spiking activities of parallel spike trains. So again, we are in the context of parallel point processes, but more an applied approach. There are different approaches. Again, some of them start already quite classically from a cross-correlation analysis, a cross-correlation histogram, which is a quite old, but again, very used approach that looks at pairwise correlation in time. There are more advanced approaches that look at the dynamics of correlations, just as the joint pair stimulus time histogram. There are approaches that look at higher order correlations, so starting from triplets of spikes detected across trials, such as the unitary event analysis formulated by Sonja Grun, but also the spatial temporal spike pattern analysis formulated by Moshe Abeles. There are already quite some experimental evidences of significant triplets in cortex, in macaque motor cortex, in a paper by Riley et al. In Science in 2006, or in Prut et al. In 1998, which again are results already that are becoming old. And then there are more advanced and recent approaches that look at higher order correlations. So starting from correlation of size order 2 on, so triplets or quadruplets of spikes. Here I listed some of them. There are many, many more, but the ones that I'm going to concentrate about are this one and this one. So maybe I should explain a little bit more, because this already looks quite a large topic, what actually we are more interested in within this project. Actually, our hypothesis in terms of the Hebbian assembly hypothesis and the temporal coding is that assembly activity is expressed by the occurrence of precise spatial temporal spike patterns with precise temporal delays between the spikes emitted by neurons that are presumably member of an Hebbian assembly. So the structures that we are looking for in the data look more like this. They can be synchronous patterns of spikes coming from neurons that always belong to such patterns. It can be synchronous, they can be delayed, as you can see here. Of course, the red dots represent the patterns. But we can extend what we are going to talk about also to propagation of synchronies that you can instead see in panel E, which can be considered basically representations of a fire chain activity. So when we want to look at this and we want to test for it, we might think of assuming a model behind it. Maybe a simple point process model like a Poisson process, and trying to estimate how many times would such a pattern occur, fixing the number of neurons and so on, and maybe an average firing rate. But unfortunately, we have to look at the reality of experimental recordings if we want to analyze them. And the reality is not so easy. So we can see from many studies done in the past that experimental data has complex features, that a complete and satisfactory analytical approach is often very hard, if not possible. And for instance, this is well represented in this paper, Mochizuki et al. Published in 2016, where they grouped together different data sets analyzed by many labs. Actually, the number of authors in this paper is quite impressive, looking still at macaque, so fixing a species, macaque cortex, but varying, actually not only cortex, but varying the area of the brain. So in this paper, they looked at the statistics that are seen in the motor cortex, in the prefrontal cortex, and the hippocampus. And they looked at their general statistics across different experiments, you can imagine. And they see that the firing rates strongly change in time. They are non-stationary in many ways. The firing rates change also across trials. The firing rate onsets or offsets change across trials, so like latency variability. And they also see that spike trains pretty much deviate from Poisson. So from the Poisson assumption, actually we can see that in more motor cortex, the data look more regular than a Poisson assumption. We can So these are interspike interval distributions. Sorry, I should have mentioned it. Less in the prefrontal cortex. Instead, in the hippocampus, data looks instead more bursty. So all of these evidence serial correlations. And this is actually why when we want to test for higher order correlations, often the case is that a model is not assumed actually, but different approaches need to be used. For example, one might decide to generate surrogates. So, and then we come to the title of the talk. Surrogates are a very classical way of generating a null hypothesis when a complex analytical description is not possible or very hard, and it consists in manipulating the data, for instance, destroying the feature that we want to test for. In this case, it's the potential fine temporal correlation, extracting one measure from the original data and from the surrogates, generating, of course, many surrogates, a large number of them, in order to derive a distribution of such measures that needs to be compared to the empirical measure that is observed in the original data. And then from the surrogates, of course, we need something to derive a significance. It can be the surprise, it can be a p-value, and so on. This is often used in general, for instance, already from a cross-correlation study that you can see here. This is a cross-correlation histogram, a cross-correlogram. There's a time lag between the central spike on the x-axis and the count on the y-axis. And what we can actually see already from earlier studies is that we can get obviously different results depending on the surrogate technique that we decide to use. So it is actually worth, before looking at our test, to vary and to choose a proper surrogate in order to derive significance. And this is what we tried to do for higher order correlations. So here I present you 6 different surrogate techniques that we decided to look at. Here you need to be a little bit concentrated, although the techniques are very easy, but they are 6. So I'm going to go through one by one. The first one is a classical approach. It is called uniform dithering. Remember that we want to generate surrogates from continuous time spike trains. Uniform dithering consists in the displacement of each single spike according to a uniform distribution of a parameter that is usually in the range of a few milliseconds for temporal coding, and it has been used in many studies. Again, this is the classical approach that does not take into account the biological characteristics of experimental spike trains. So one might decide to incorporate some of those biological characteristics and extend this method. We decided to, on our own, to extend the classical uniform dithering by just incorporating the dead time. The dead time, that is the refractory, biologically speaking, the refractory period of the neuron. It is hard to estimate also mathematically, but it can be enforced sometimes by the spike sorting algorithm. And basically this adapted approach consists in displacing each spike by uniform distribution, but still keeping a time constraint between successive spikes such that the dead time is not violated. Our next approach that is more advanced is what is called the joint interspike interval dithering, which was designed by George Genstein in 2004. And this technique displaces spikes according to the joint interspike interval distribution of adjacent interspike intervals. So adjacent means one after the other. So we have the first interspike interval on the x-axis, the second interspike interval on the y-axis. We sample all these interspike intervals from our original spike trains, and then we use this distribution to sample surrogates. So this has the nice characteristic that it preserves many statistics, such as the interspike interval and the joint interspike interval distribution. But of course, we need enough spikes to estimate such a distribution. So this is a quite advanced approach that can be simplified by also looking only at the interspike interval distribution. So taking into account how we sample the joint interspike interval distribution, we can just replace this distribution with the outer product of the ISI distribution. So just sampling based on the interspec interval distribution, not keeping the joint, but still the approach is quite similar to the previous. And it also leads to good results. We will see it afterwards. The next approach is also, again, quite easy. It's called trial shifting. It consists in, instead of shifting each single spike, in shifting the entire spike train. This is particularly powerful if we have data that is segmentable, meaning that we have a standard experiment where we have trials. The animal is doing trial after trial. So we shift each trial, single trial, and each neuron independently by a uniform distribution. This has the nice characteristic that it preserves mostly all statistical features, of course, because the spike train is just shifted. And then finally, the last approach is a discretized approach. So meaning that very often when we want to look at and evaluate correlations in continuous time spike trains, we often do it on the discretized version of the process. So the discrete process, like a 0-1 process. So we might think in this context of just shuffling locally the bins, the bin contents, so shuffling the spikes within a window that can be a tiny window, given that we are testing for temporal coding, so we want to keep the firing rate profile preserved, and it's also algorithmically simple. So again, I presented all 6 of them. They're already over. And maybe I want to say why we want to use them. So of course, we want to detect, as I said before, spatial temporal spike patterns in parallel spike trains, but I haven't said how we do this. So there's a technique that we have developed over the years that we call SPADE. It stands for Spatial Temporal Pattern Detection and Evaluation, and is able to find such structures in parallel spike trains. So these are 2 patterns, actually 1 pattern occurring 2 times across these 4 neurons over and over and identically. SPADE combines an optimized mining technique that is called frequent item set mining that looks for patterns in spiking data, and then tests such patterns for significance, obviously using surrogates. So maybe a little bit in a detail exactly how SPADE works. I can show in this figure. So spiking data is given as input. It's subjected to discretization and then mining of such patterns with the mining technique that I was saying to you before. Patterns are collected, and then since we don't want to test each single pattern because they are evidently many in such large data sets that we tend to analyze, we decide to group them due to their statistics. So basically we group at patterns depending on their characteristics, of their order of correlation, and on their temporal duration. And then we do the same thing on the surrogates, of course. We collect all these statistics, collect them in a p-value spectrum, basically evaluating in how many of the surrogate datasets we find patterns that were detected in the original data. We divide by the number of surrogates, we correct for multiple testing, and then we get a p-value that we use for testing. After a second conditional test on the patterns that I don't want to talk about, we get significant patterns in return. So what I want to show also in this figure is that we can use different surrogate methods. And actually what we want to show is that we get different results, and why it is important to use a proper surrogate methods for such estimation. So why did we decide to do this? The classical technique, the uniform dithering that I was explaining to you before, already gives some problems when applied to experimental data. Basically, we saw that the application of uniform dithering, again, it's the temporal displacement of each single spike locally, applied on experimental spike trains, if the data are discretized, which is often done, leads to a reduction in the spike count. Not only this, which is already quite troublesome for statistics in general, but also that many of the intrinsic characteristics of the original spike train are disrupted. For instance, the interspec interval becomes more exponentially distributed. The dead time is not preserved, the regularity of the experimental neuron is not preserved. And all these effects get stronger with increasing firing rate, which is often the case in the motor cortex, which is the area that we are interested in. So when we found this, we decided to investigate further which are the reasons for this. And I can show you very briefly as a sketch what happens in practically. Basically, if the original spike train has a dead time, some sort of regularity, for instance, intrinsic regularity of the spike train, firing regularity estimated with the coefficient of variation, or simply a dead time, it can happen that by the moving uniformly this spike, actually all spikes, it might happen that they end up in the same interval that it used for the discretization. And thus, this leads to a reduction in the spike count. If you see here, we have 8 spikes that we end up, obviously here, we want to give the idea, we end up having only 4. So we decided to model this analytically, so a little bit of math, by using 2 spike train models. The first one is a Poisson process with dead time that was introduced by Deger et al. In 2012, and by a gamma process. We decided to derive analytically the spike count reduction and function of the firing rate for the original spike train and its surrogates. This can be done quite easily, actually, from the distribution, the interspec interval distribution of these 2 processes by varying the dead time and the gamma parameter of the gamma distribution. And by looking at the surrogates here dotted and the original spike trains, we see that there's a mismatch in the spike count. And the consequence of this is quite dramatic, because when we try to model this by looking at distributions of patterns found in ground truth data, meaning different realizations of processes, and by looking at their corresponding surrogates, we see that there's a shift in the p-value distribution, meaning that there's an overestimation of significance that leads to false positive detection. Obviously, we do not want to detect false positives, so we need some alternative techniques to the uniform dithering. This is actually why we introduced this alternative 5s, and it gave us the opportunity to see what happens when to look at the statistics of the surrogate techniques when we vary the surrogates algorithm. So first, we started looking at homogeneous data, stationary data, 3 simple models: the Poisson model, the Poisson process with dead time, and a gamma model. We studied some of the statistics by varying the surrogate techniques, for instance, the spike count, the interspike interval, autocorrelation, surrogate independence, and so on. This figure is, I admit, quite complicated, so I want to give you an easier interpretation by looking at a table that shows basically which of these characteristics, which of these statistics are kept and which are not preserved by each different surrogate technique. So as we can see right from the beginning is that uniform dithering does not preserve many of these statistics, which are important for us as we are testing for, again, temporal coding. So the more characteristics of the original spike train preserved, the better for robustness of any test. But we can also see is that different techniques preserve different statistics. And there's in particular one winning technique, which is the trial shifting here, that in the case of homogeneous data preserves most of these statistics, basically just by definition. So this is already quite nice result and is quite satisfactory. Of course, the problem is that, again, as I said from the beginning, we were only looking at stationary data, which is not applicable to experimental recordings. So we decided to actually generate data that are non-stationary, and we decided to model 2 sessions of an experimental data set published in 2018 in the laboratory of Thomas Brochier in Marseille, with these 2-point process models, the Poisson process with dead time and the gamma process. We estimated the non-stationary firing rates neuron by neuron, trial by trial, very finely. We estimated the coefficient of variations and turned it into a parameter of a gamma process, and we estimate the dead time for each single neuron in order to have data sets that look like experimental data but are otherwise independent. So if we look for spatial temporal patterns in independent data, we should find few false positives, of course. Some of them are all need to be there because it's a statistical test, but we don't want to find many. And what we see when we apply SPADE across different surrogate techniques is that uniform dithering leads to a large number of false positives. And this is obviously not good, whereas the other surrogate techniques almost give the same number of false positives beside uniform dithering with dead time, which is not really great for gamma process. So more false positives are actually more detected for the Poisson process with dead time when the intrinsic irregularity of the neuron is not included in the model. Furthermore, we looked at the characteristics of the neurons involved in false positives. Mainly, we found that neurons that have a firing rate higher than 20 Hertz and the coefficient of variation lower than 1, actually CV2 because the data are non-stationary, tend to be more involved in false positives, whereas very regular neurons, neurons with low firing rate, and neurons that are bursty are not involved in false positives. So taking into consideration all these results, we can identify that pretty much all these surrogate techniques are good for us. But of course, given the results on stationary data, we might prefer the trial shifting for our purposes. And finally, I want to give you a short glimpse of an application of experimental data that is quite interesting. So again, it is the same data set that I was referring to before. It is an experiment done again in Marseille in the lab of Thomas Brochier. There is a 10 by 10 Utah array electrode implanted in the pre and motor cortex of 2 macaque monkeys that are doing a reaching and grasping task. Basically, they are pulling an object that you can see here with 2 different grips. And we want to detect spatial temporal patterns that are locked to the behavior of the monkey. So we segment the data accordingly, and we are able to look at these 2 different monkeys, 2 different sessions on different days, and vary the surrogate technique. Of course, here we do not have a ground truth, so we are not able to see whether these are false positives or not. But what we see is that, again, uniform dithering leads to a large number of patterns detected that due to the results that we obtained before, we tend to discard as putative false positives. Whereas we find many patterns by using the different surrogate techniques that I showed you before. And actually, we find more patterns than, of course, false positives, which is very nice. Actually, almost double or triple the number. And these patterns are very similar across surrogate techniques, lead to basically the same significance threshold, and overlap in their neuronal participation. So basically, they are the same patterns, which gives us a very nice conclusion in terms of robustness of our findings. My time is over, so I conclude. We hypothesize that the assembly activity, Hebbian assembly activity, is expressed by spatial temporal spike patterns in parallel recordings that are emitted by neurons that are presumably member of such an assembly. So to detect such patterns, we have developed a method that does so and took into consideration 6 different surrogate techniques. We see that the classical surrogate technique that is often used together with spike train discretization leads to a strong spike count reduction in the surrogates. So we decide to study the statistics of these alternative techniques analytically and through simulations. And we see that when applied to non-stationary data, uniform dithering leads to a large number of false positives. And concluding, one of the methods that we propose, trial shifting, is our preferential method for the evaluation of the significance of patterns in parallel spike trains. I thank you all for listening. I thank my group of statistical neuroscience in ULISH and my supervisor, Professor Sonia Grun. Thank you so much for the patient.
Thank you for the presentation. Are there questions or comments? Write on the chat if you don't have the possibility of switch on your microphone. If no one has comments, I want just to give a small comment. You will say that the uniform dithering is moves the distribution toward the exponential behavior. And
yes.
This looks to me very natural because somehow uniform dithering is a way to delete any form of memory in your spike train, and the exponential behavior is the zero memory instance. So I think that any type of dithering will somehow try to destroy this the different behavior of the tails.
Yes. So unless you specifically design a technique, for instance, as George Genstein did back then, to preserve the interspike interval distribution, pretty much any interspike interval structure is disrupted, which is, yeah, obviously a problem. Of course, if you want to preserve it too much,
you don't get information.
You don't get information back. Yes.
Yes. Yes, it's true. Sure. Any further comment? No. Otherwise, we thank again Alessandra.
Thank you.
And we switch to the next speaker. He is Ryota Kobayashi from Tokyo University. And
thank you very much.
Will be somehow in between statistics and modeling. He will speak about estimating synaptic connectivity from parallel spike trains.
So I will share
your screen.
Yes, screen. Yes. Okay.
Yes, perfect. We see it.
Thank you very much.
And we see your mouse if you want to use it.
Yes. Okay. Thank you very much.
Please.
Yes. Hello everyone. Good afternoon and good evening. I'm Ryota Kobayashi, and first of all, I'd like to thank Professor Spatial Dorote for giving me the opportunity of this talk. And today, I first explain, this is outline, and first I explain now why we are interested in estimating synaptic connectivity. And then we introduce two methods for estimating the connectivity from spike data. And finally, we discuss how this method performs to artificial data set. Okay, so let's go. And so as you know, our brain is a network of neurons. That is, the brain consists of a huge number of neurons, and the neurons are interacted via synapses. And here we focused on an important research question, how these neurons are connected and how they are interacting during information processing. And before going to the question, we summarize the key players, neurons and synapses. Okay. And this is a schematic of the neuron. And as you know, neuron is a basic element in the brain. And the neuron receives a fluctuating input from thousands of excitatory and inhibitory neurons. And also due to the input, the voltage, especially for the behaving, the neurons in the behaving animals, the voltage fluctuating, and they generate spikes. And so roughly speaking, the neuron is a sort of the stochastic unit, and the neuron generates spikes when the voltage reaches a threshold. And and this figure shows how the neurons interact via synapses. And an excitatory neuron, shown in this magenta, transmits a positive current that pushes the voltage of the postsynaptic, this neuron. And when presynaptic neuron, yes. And similarly, if the neuron is inhibitory, they generate a negative current which inhibits the neuron. So the neuron interact so via voltage, not spikes. So in this talk we focused on spikes. So the important things is the interaction is somehow stochastic if we have only spike data. So it doesn't affect spike directly. Okay. And one important information is the one good news is there is a greater advances in decoding neurons. And the number of neurons which we can decode simultaneously, and number of the recording duration are also continuously increasing. And this is a log plot about the papers which records multiple neurons. And the x-axis is a publication year, and the y-axis is how many neurons they collected simultaneously. And you can see nice log plot. And interestingly, there is exponential growth in the number of recorded neurons in every 7 years. And now recently we can record up to 10,000 of neurons. So this is this is a very good time to working for such a massively collected multiple spike trains. Yes, and this is a program we focus today. Let's assume we record spikes from a part of our brain, and it is shown in the colored neuron, magenta and cyan. And we recorded spike trains from these guys, and we want to infer the synaptic connectivity between the recorded neurons. And in the next section, I explain how to do it. Okay, so then we explain, we describe the methods for estimating synaptic connectivity from spike trains. And first of all, I explain the most standard method, the cross-correlation for estimating the synaptic connectivity from spike trains. Note that it was originally proposed in 60s, and it is much older than me. Yes, and this is a schema. This slide explained how to do it in cross-correlation. This method is a pairwise method. So if we collected hundreds of neurons, we always focus on each pair for estimating connections. So let's focus on the pair of neurons, which we call reference and the target neuron. And R1, R2, R3, R4 represents the spike times of the reference neuron, and the T1, T2, T3, T4 represents those of the target neuron. And this method first calculates the cross-correlation data. This is first we focus on the first spike of the reference neuron and calculate the reference time, S, and we obtain the sort of the transformed spike train of the target. Then we move to second spike, and we calculate Tj minus R2, and we have a second and transformed spike. And by repeating this procedure for all the spikes of the reference neurons, we have cross-correlation data. It is target spike train shifted by each spike time of the reference, of the spike time of the reference neuron. And using this cross-correlation data, we construct a histogram of the, we counted the number of spikes of the cross-correlation data, and we construct a cross-correlation histogram. And how many neurons fires, for example, just after the spike of the reference neuron, and so on. And this is quite interpretable, and because the peak around 0 indicates the connection between these neurons, and the valley, if we found a dip here, it represents inhibitory interaction between the neurons. And if you found a peak in the right side of the plot, there is it indicates the connectivity from a reference to target. And if you find a peak in the left side, it indicates again the connection from target to reference. So it is quite easy to implement and easy to interpret. However, there is a problem, and this method is quite, as I explained, relatively simple and easy to implement. But this method and also applied to various data sets, and we found many interesting things. However, this method has a drawback. It is vulnerable to large fluctuations in neuronal activity, which can be problematic if we are interested in the spikes recorded from behaving animals like me. And this is an example recorded from walking rat CA1. And this detected peaks based on cross-correlation method, significant peaks are shown in red circles. And you can find 2 peaks and 2 valleys. But we can see that this peak may be connection, but it's not clear whether this valleys and this peak is really synaptic connectivity or not. So to overcome this difficulty, of course, there are several attempts. And one method is actually introduced in the previous talk with Dithering. It is also called the Dithering method. However, this method is not enough to solve this problem in animals, in the spike strains in the spiking data set. So we want to develop new methods for estimating synaptic connectivity. And this talk, I propose 2 extensions of the cross-correlation methods that overcomes the difficulty. It's a vulnerability to large fluctuating neuronal activity. So 2 methods is called GLMCC and Connect. First, I start from GLMCC. And this method is a combination of generalized linear model of a point process and the cross-correlation method. And so the basic idea is shown in this figure. We first generate a cross-correlation data, but we didn't construct histograms. Instead of constructing a histogram, we fit generalized linear model, which considers the input from neighboring neurons, shown in green. So our GLMCC method considers the external input from the neighbors. So, and this idea is shown in this slide, this idea is shown using equation. And we fit the cross-correlation data using this model, this type of point process model. And AS represents the input from other neurons. It can fluctuating freely. And J plus, this is a connection from a reference neuron to target neurons. And J minus, this is a connection from target to reference neurons. And the kappa is an exponential function with delay, so which models the synaptic interaction between two neurons. So by fitting this model, we can have the estimate how we can estimate the strong the connectivity between two neurons. And this is the result. And you can see this is a result applied to the CA1 data. And you can see this DLMCC works nicely to this data set. And so for this procedure, we find the parameters AS, J plus, and J minus. And after finding parameters, we detect significant connections. This is done by likelihood ratio test. Simply, we calculate compare the likelihood, which we consider the connection, and we didn't consider the connection. So if we didn't consider the connection, so this model explains everything with input from the neighbor, something like that. And we follow the standard procedure for the likelihood ratio test. So this is the GLMCC. This is a combination. That method is a combination of point process model and the cross correlation. And the next model, we explain the connect. This is a combination of the cross correlation and the neuronal networks. And we infer brain using neuronal networks. And this is this figure explained how to do it. And as we explained, we construct a cross-correlation histogram. And the key idea is we transform this cross-correlation histogram to image. Because so if so this histogram can be considered as a histogram, as an image of a black and white. So the higher count means more black, and the smaller counts means more white or something like that. So, and if we transform the images, we can use neuronal networks, which is now quite strong for analyzing image processing. So we applied image processing neuronal network, and we trained the neuronal network whether this figure corresponds to the connected or not connected, something like that. And let's explain the result of these methods. And to validate this method, we simulate the population of neurons. And for this simulation, we simulated thousands of neurons. And and 800 is excitatory and 200 is inhibitory. And we connected random connection, and each PSP follows log normal and normal or something like that. It's something for it's considered to be physiologically relevant. And we obtained asynchronous irregular state, which is considered realistic. And from the simulation data set, we originally have thousands of neurons, and we assume we only recorded 20 neurons from the thousands of neurons. And from the spike train of 20 neurons, we tried to infer the connectivity, and this is the result. And since we simulated the network, so we have the true connectivity. And this matrix and the true connectivity matrix is shown in this figure. And the magenta means a positive connection. And this area represents the strongness of the connection. So this connection shows a strong connection. And the cyan means the inhibitory connection. And again, the size of the square represents the amplitude of the connection. And you can see, and the bottom plots, we calculate the number of total errors in the 2020 neurons. So you can see while these previous methods relatively high number of errors, this GLMCC is smallest. And you can see the Dithering method is the method tends to be very severe to detect a connection. So the detected number of connectivity is very small compared to the true connectivity. And we also repeated this validation using various data sets. And you can see GLMCC and Connect. The performance is somehow comparable. This is simulation data from MAT model, and this is again Hodgkin X-ray. And for MAT model, Connect is slightly better. And for Hodgkin X-ray model, GLMCC is slightly better. But again, these two methods is much better than cross-correlation and the Dithering method. Okay, finally, we want to explain, we want to show the web application for the experimentalists. And let's share another screen. Can you see?
Yes, now.
So this is a web application for our algorithm. And this is relatively simple, just uploading data and select data and connect and push the button. And this is a result of our web application. And again, this shows the connectivity, the magenta shows the positive and the cyan shows the negative. And the color strong magenta shows a strong connection. And you can create a network if you have spike train data. And we can apply various methods, GLMCC and Connect and something like that. And you can also check the cross correlation using the web application. So please, if you are interested, you can play with it. So I now sent the information to chat. And the Python application is also applicable. So if you are interested, you can play. Anyway, so let's return to my presentation. And so as I explained, we developed this method. And finally, before going to the conclusion, we want to discuss the pros and the cons of the proposed two methods. So the conclusion is that these two methods are somewhat complementary, because the GLMCC method is based on cross-correlation method. So we can easily check the result. So the estimation result is somehow interpretable. But unfortunately, this method needs to choose some parameters for each dataset. It's somewhat difficult, and it can be somewhat tough for experimentalists. On the other side, the Connect is easy to apply the dataset because it was already trained. So just to push the button. But unfortunately, the Connect, everything works in the neuronal networks, and we don't know how it works. So the estimation result is not interpretable. So these are, I think these methods are complementary. Okay, sorry. So summary, this is a summary. Today we explain two methods, GLMCC and Connect, for estimating synaptic connectivity from spike trains. And these methods can estimate the connectivity more accurate than existing methods. And the web applications and the Python codes are ready for your analysis. And thanks for your attention. And finally, I would like to thank for all the collaborators here. Thank you very much.
Thank you. I see some questions.
Yes.
So the first is from Ost. I was wondering whether the methods you presented can be applied for partially observed network of neurons. Could you comment about this?
Yes, as I explained, maybe my explanation is not good, but indeed, we investigate the partially observed scenario. So we simulated thousands of neurons, but we assume we have only 20 spike trains of 20 neurons. So I think this situation, this scenario is exactly the partially observed network. And even this situation, GLMCC and the Connect can estimate, of course, not perfectly, but they can estimate much more accurate than the existing methods. Thank you very much.
The next question is from Pascal Helson. I did not understand how you can infer inhibitory connections from cross-correlogram matrix. If I understood well, spikes from reference to target need to cause spikes of the target cell in order to decide there is a connection from reference to target. In the case of inhibitory neurons, we do not expect such a causality. Am I wrong?
The inhibitory case, we also somehow, maybe there is some example. Inhibitory case, we somehow expect, this is an example. We can see small, some valley dip. So we assume inhibitory neurons decrease the number of spike count just after the spike. So in this sense, we assume causality also for the inhibitory neurons. But this method but our method might not work if our method doesn't work if these neurons doesn't fire at all. If zero spikes, no inhibition. But all the methods cannot estimate it. Thank you very much.
I see Alessandra has a question. Please, Alessandra.
Yes, I prefer to speak if possible. So I wonder if you are aware of a similar technique that was published in 2016 by the Scherberger lab in Germany. They use CCHs from actual experimental data. They evaluate them for significance, and then they basically construct a graph from them in order to study the topological properties of such graph. In that case, since they have floating electrodes, they cannot talk about a direct, let's say, connection between neurons. They call it functional network topology, but I think in design it's similar to yours, and I think this is really interesting. But my question is, because I tried last year with some colleagues of mine to actually apply their technique to our data across different electrodes, and what we observed is that we needed a lot of data to estimate such, for instance, dense cross correlations, and sometimes it is not possible because you have finite data in experiments, and I wonder if instead this would partially solve our problems, because maybe we need less power for doing such a test. If you ever try to apply it on parallel spike trains that come from experimental recordings.
Yes. And at least we applied already. So already in this paper, for example, we applied data from RAT CA1. And in that case, we applied the data from 90 minutes recording.
Okay.
It's a relatively lot, and but we checked some strong connection can be extracted from 30 minutes.
Okay,
recording.
that's really good. Thank you.
That's
really
and
helpful.
Also the second paper this one connect paper, we applied 20 or 10 minutes recording from a monkey, and it is somehow they at least this method returns some answers. So
okay, yeah.
Please apply if you are interested.
Yes, thank you.
And,
thank you so much.
Yes, and if you have some issues, please tell me. I'm happy and to work on that. Yes.
I see a last question from Dimitra Mutka. Have you compared how the performance of GLMCC compares to plain GLM methods?
Yes. Yes. We also compare the GLMC. Originally, we worked on GLM methods, and we compare the performance, and we at least we found that GLMCC method is much better, and it's especially useful when the data has a large fluctuation, like experimental data. Thank you very much.
Hans, I think it's time. Thank you again, Ryota, for this talk that moved a lot of questions.
Thank you very much.
And we can switch to our last speaker, that is Massimiliano Tamborino from I'm lost, Warwick University. Okay. Many Italians, but around the world, plus a non-Italian who mimetize.
Can you see my screen?
Yes, we do.
Okay. Well, thank you for being here, despite being the last talk of the session. Well, good afternoon or good evening, depending on where you are, everyone. I'm Massimiliano Tamborino, and what I want to present is a work with Petr Lansky. The title of the work is Shock Noise, Visual Approximation, and with convergence. It's a kind of weird feeling to present this talk, because it's a joint work with Petr, who recently passed away in April, and it's not so easy to do this. Petr has been more than a reference and a scientist person for me. I met him 10 years ago when I was a PhD student in Copenhagen. I spent almost 4 months in Prague working with him, where I also had the chance of meeting Ryota there and spent some time there. And since then, we have been working intensively, especially after I moved to Linz in Austria. We won a couple of grants together. We were visiting each other a couple of times per year, either in Linz or in Prague. And this is a work that we started when I was still in Linz, and we submitted last year, and has now appeared in Physica D this April. Okay, so the talk is devoted to Petr. I want to talk about the Poissonian short noise process. So imagine to have the following setting. We have some process which starts from some position x0. In case nothing happens, it has an exponential decay towards it. Alpha is the parameter determining the exponential decay rate. There is an underlying Poisson process NT, which is the one describing and moving the dynamics. So anytime there is an event coming, there is a jump. The jump has some random amplitude jk, where k is the k jump. Tau k is the time of the jump, and these jumps are assumed to be modeled by non-negative random variables. They are IAD, distributed as some random variable j, and they are independent on the underlying Poisson process. If you are more familiar with SDE, you can rewrite this expression as dxt equal to minus alpha xt dt plus j dnt. And well, actually, why is the short noise important? Well, it has been initially proposed as a model for describing the membrane voltage in leaking integrated amplifier models. If you are familiar with the leaking integrated amplifier literature, this looks like a sort of Stein model where there is no inhibition, right? In the Stein model, you will also have plus j minus dn minus t, so plus some negative component pushing down. So if you think about Ryota's talk before, it is like saying that there are only excitatory postsynaptic potential. More recently, it has been used as a sort of building brick into more advanced models, like, for example, it is used to describe synaptic input currents in integrated amplifier models or leak integrated amplifier models, as well as describing the conductances into conductance-based models. So in a way, the short noise process might not be definitely the most used and the most sophisticated models if you want to model the membrane voltage. We all agree on that, but it can be used as a relevant component into integrated amplifier and conductance-based models. What is important is that no matter which setting you are familiar with, no matter which setting you are interested in, the mathematical formulation of the short noise process is the same. So whatever I'm going to say later is valid, okay? So the setting of interest is the one where there is some underlying Poisson process NT, as I was mentioning before, and we are interested when there is some large jump frequency, or if you prefer, if you're thinking about, again, modeling this as excitatory postsynaptic potential, there are a lot of stimuli, a lot of currents coming. So there are a lot of them. The jumps are happening at an increasing frequency, and the amplitude of these jumps is decreasing. So if we have the jumps to be random, as in our setting, then it corresponds to say that the expected value of the jump amplitude decreases. A common approach corresponds to say, well, let us imagine that this jump frequency is large but finite. What we can do is to compute the underlying first and second infinitesimal moment of this discontinuous process and replace them by a diffusion process. So if we do that, what we obtain is this SDE of this Y tilde solution, and you will immediately recognize that this is an Orsten-Uhlenbeck process, okay? Here, the drift comes from the interaction between the expected value of the jump amplitude and the frequency of the jumps. However, if you are also thinking about what I told you before, we are assuming to start from some initial position x0, which is positive. We know that there is an exponential decay towards x0, and the jumps are only going up, right? So that means that this non-negative Poisson short noise process has a state space between 0 up to plus infinity, meaning that it cannot go below 0. So the Orsten-Uhlenbeck process, which has a state space R, does not seem to be a plausible or a good approximation. And so not surprisingly, when people were trying to replace the shot noise process with the Orstenulen process into these more advanced models, they got a poor approximation. So what I want to do today is to derive a more mathematical rigorous approximation under some suitable condition that I'm going to define later. I want to show you how the derived model is going to outperform the approximation that we would have get by using the Orstenulen process, and also give you a bit more of motivation why the Orstenulen approximation is not the best one. I already emphasized the fact that there is a difference in the state space, but there are more mathematical motivation behind this. So in the following, I'm going to consider sequences of shot noise processes. Let me emphasize strictly that these are non-negative shot noise processes. So I'm assuming, once again, these jumps to be strictly non-negative, okay? And I'm in the setting where the amplitudes, the expected amplitudes of the jumps goes to 0 while their frequency goes to infinity. So this would be the classic setting of a diffusion limit if you think about random walk converging to a Brownian motion, okay? So the two questions that I want to answer are, the first one is, what type of limit process do we get for such a sequence of shot noise processes? And moreover, if we do not care about the limit, but we want to work with a large but finite jump frequency, what could be a better approximation than the Orstenulen process, okay? There are a few results. Basically, you can manipulate the original shot noise process in a way of getting any sort of limit, depending on what are your interests. But what I want to do is to work with the original shot noise process. So I don't want to do any sort of manipulation like subtracting the drift and rescaling by the standard deviation and so on. So the outline of the talk, I first want to recall different types of limits and approximation. This is particularly relevant because when I first got introduced to the topic with Petre, I was kind of confusing because when reading different papers, they were using the same notion of, well, the same name of diffusion approximation for quite a different notation and quite a different notion. So I want to reconcile this. Then I want to derive the so-called weak convergence of the sequence of shot noise processes, and I will define in a second what does it mean. I want to characterize the feature of the limit process, and then I want to discuss under which condition the sequence of shot noise processes can yield a diffusion limit, so we can get this back, this Orstenulen process. I want to compare the different approximation, and then if time is left, there is an open conjecture that we weren't able to prove, so hopefully you can help us on this. So what I was mentioning before is what we define the usual approximation, and is based on the idea of basically equating the infinitesimal first and second moment of the discontinuous process with a diffusion process, okay? And if you do that for the shot noise process, you will recover the Orstenulen process. So in this case, no limit is taken, you just equate the first two infinitesimal moments. If you are also imposing that the diffusion process has to be a Gaussian process, we have what we call the Gaussian approximation, okay? So in the case of the shot noise process, both the usual and the Gaussian approximation yields, in fact, an Orstenulen process. Part of the confusion I had in my mind, but also talking with other colleagues like Magnus Richardson, but also Benjamin Lindner, was the fact that these two types of approximation are sometimes known as diffusion approximation in our community, as also, for example, in the mean field community. While I had in mind a different notion of diffusion approximation that I will explain in a second. So to avoid this confusion, I refer to this type of approximation where basically you want to equate the infinitesimal first and second moments as usual or Gaussian approximation. The third type of approach is the one that yields the fluid or the thermodynamic or the hydrodynamic or the hydrodynamic limits, or also the Langevin approximation or Kurz approximation. Once again, for fixed n, you are equating the first two infinitesimal moments, but then the difference is that if you do the limit and n goes to infinity, what you are going to obtain is a deterministic process. So if you do, I mean, this is also quite common in mean field theory. You have a lot of neurons, capital N. You approximate this collection of discontinuous processes by a diffusion process, and when n goes to infinity, you will obtain back the deterministic process. So this is also sometimes called as the Langevin approximation or the Kurz approximation. But this is also referred as sometimes as diffusion approximation, which makes, again, everything a little bit more confusing, okay? So from a mathematical point of view, what I want to study is the so-called weak convergence of stochastic processes, which corresponds in studying those triplet of characteristics that Bruno was introducing in his talk. And it's a mathematical way of saying, well, let us look at this process on itself and what does it happen, how this process converge in terms of laws or the distribution of this process when n goes to infinity. And you either prove it via the convergence of triplets of characteristics, as is proved by Jacob and Shirayev, or you can also show via the convergence of the finite dimensional distribution and some regularity condition like the tightness. Okay, so this is the most mathematical approach somehow. It can yield any sort of limit. There is no condition, no prerequisite on the type of process, limiting process that you get, but it's not that easy to handle. Another approach is the one that we refer as diffusion limit, but it was initially proposed, initially called by Ricciardi and his co-workers, including also Laura, as a diffusion approximation. So if you have a one-dimensional process, as we have, proving that proving the weak convergence, so proving the convergence of these processes via the triplets of characteristics, can be done in a way easier and way more manageable way by just looking at the convergence of these finite dimensional moments. Okay, so in particular, you have to show that the first and the second infinitesimal moments converge to the limiting process, and that the fourth infinitesimal moment vanishes. The fact that the fourth infinitesimal moment vanishes means that the limiting process is going to be a process with no jumps. So it's going to be a continuous process, meaning that you are going to get a diffusion process. So this is why it's called diffusion limit, or in a way, weak convergence to diffusion process. But it is also known as diffusion approximation. But you will agree with me that this notion of diffusion approximation is different from the previous one. Here, there is a rigorous mathematics limits, and if under some condition, you are going to get a diffusion process. In the previous approach, in the usual or the Gaussian approximation, such limit does not exist. You are only comparing infinitesimal moments. And in what we call Kurz approximation, when actually you do the limit of n goes to infinity, you obtain a deterministic rather than a diffusion process. So we are interested in deriving the weak convergence of these sequences of short noise processes. And well, the previous component, this J, D, and T, could be replaced by a component Poisson process with some Levy measure that is basically nothing else than the product between the intensity of the jumps and the distribution of the jumps. So the frequency of the incoming jumps of the Poisson process and the distribution. And if you do not really like to think about the measure, you can think about the density, where basically you replace the CDF with the PDF. Okay. So what we were able to show is that if the intensity of the jumps goes to infinity, and the Levy measure of the sequence of the shot noise, so the Levy measure of this compound Poisson process, converge to a Levy measure, what we get is what we call well, what is known as a Levy-driven or Stenulenbeck, which is the solution of this STE, where now the compound Poisson process is replaced by its limit, where this limit is characterized by a Levy measure, which is the one obtained by doing the limit. So things seems quite hard, but in fact they are very simple. You take your jump distribution Jn, you compute its density, you multiply this density by lambda n, so by the frequency of the jumps, and you do the limit when n goes to infinity. Okay? If you get something finite, this is going to be the Levy measure of your limiting process. Okay? And actually it's going to be the Levy measure of this L infinity, which is also known as the background driven Levy process, because it's going to act as a sort of underlying noise. That's why it's called background driven. Okay. What we show, which is somehow not so surprising, it's relatively intuitive, is that such a limiting Levy driven or Stenulenbeck is not a Gaussian type. What does it mean? It means that the underlying Levy process is not a Brownian motion, meaning that this process is not an Orstenulenbeck. So it's not a Gaussian Orstenulenbeck, but is a non-Gaussian Orstenulenbeck. Okay. In particular, one can show that it is not true that this Levy measure converges to zero. Well, we will need the convergence to zero to show that actually there are no jumps, so the process is a continuous process, so a Brownian motion. Okay, so if we do this theoretical rigorous approach, we ended up obtaining an Orstenulenbeck process, which is very similar to the one that we are used to, but where the Brownian motion is replaced by this Levy process. We are able actually to characterize this limit Levy-driven or non-Gaussian Orstenulenbeck process. We are able to compute its mean, its variance, covariance, but we are also able to compute the characteristic function. So one may numerically invert it to get the PDF of such limited process. And you see that, well, if you look at the corresponding quantities for the shot noise, they are very similar, with the difference that this quantity here are replaced by lambda n, the expected value of the jumps, and lambda n, the expected value of the second moment of the jumps. But what is important here is that this L infinity 1 is the this background driven Levy process at times 1. So how can we study it? Well, as you may imagine, and also as we know from here, this underlying Levy measure fully depends on the distribution of the jumps. So what we have is that, well, if the initial jumps are Poisson or Bernoulli distributed with some certain parameter, we can obtain that the underlying Levy process is a Poisson process. If the jumps are gamma, we obtain a gamma process, inverse gamma process, beta, and beta process. So since the underlying processes are like this, we are going to get the non-Gaussian Orstenulenbeck is a Orstenulenbeck Poisson process, which is in fact a different shot noise, or gamma process, inverse Gaussian, and so on. Thanks to this, we are able to explicitly derive the first and the second mean of this quantity. L infinity 1 is going to be Poisson, gamma, or inverse Gaussian distributed, depending on the different setting. A first tricky thing to realize is that if we think about the gamma process or the inverse Gaussian or the beta process, they are infinity activity processes. What does it mean? It means that no matter how short you are considering your time interval, there are infinitely many small jumps happening in that interval. So what does it mean? It means that if we integrate the Levy measure, it's not finite, but it's infinite. So in this case, what one does is to introduce a sort of CDF or survival. So you are going to integrate the Levy density, and this quantity, which is called the Levy-Khinchin tail function, is going to be finite. So what does it mean? It means that if we take any small quantity x larger than 0, the rate at which jumps are of size greater than x occur is always finite. But the tricky thing is that since there are these processes which have infinity many small jumps in any time window, it might be tricky to simulate them. But luckily, this is not the case thanks to some results by Ku, Dacios, and Zhao, who were able to propose some exact method for simulating these Orsten-Uhlenbeck gamma process and Orsten-Uhlenbeck inverse Gaussian processes. So what I did was I luckily got the MATLAB file. I made it an RCPP, so just to speed up the simulation. And then there is a GitHub code available here for simulating these, both the shot noise processes with the different jump amplitudes, as well as the limiting non-Gaussian Orsten-Uhlenbeck processes. What you see here is that, well, the red line is the shot noise process, the black line is the simulation of the Orsten-Uhlenbeck gamma. They seems to behave similarly. It seems like also the shot noise has some very small jump amplitudes, but if we zoom in, we see that this is not really the case. So we can see that for the limit Orsten-Uhlenbeck gamma, there are in fact a lot of small jump happening as well as large jumps, while this is not the case for the shot noise, because we are in a setting where the intensity is small. So if we let lambda increase, then we will observe a more similarity between the shot noise and the limiting Orsten-Uhlenbeck process. And let me just, well, I don't have that much time left. Let me just emphasize what are the conditions for obtaining a diffusion limit. Well, if we want to get that the Orsten-Uhlenbeck is the limit of a diffusion approach, so it's a diffusion limit, we need to require that these 4 conditions are fulfilled. And we have already seen that if this is possible, then we will have get the Orsten-Uhlenbeck as a limit, and this is also the result of what I call the usual of the Gaussian approximation. But before I told you that this is not the case, so I told you that this limit process is not going to be Gaussian, meaning that at least one of these 4 conditions has to be neglected. Well, at least one of the 4 does not hold. Okay, so all 4 conditions do not hold simultaneously. This is our conjecture that unfortunately we were unable to prove. So if you have any idea on how to prove that you cannot find a non-negative sequence of random variables and a sequence of numbers lambda n such that these 4 conditions are simultaneously fulfilled, just get in touch with me. Okay, let me just show you the quality of the approximation. So what you see here are different results obtained via simulation of 1 million, well, 1 million Monte Carlo simulation for lambda equal to 1000. And what I'm reporting is the estimated density of the shot noise in black, the limiting non-Gaussian Orsten-Uhlenbeck process in gray, and the Gaussian Orsten-Uhlenbeck process in blue, when t is equal to 1 and when t is equal to 100. So the setting t is equal to 100 is under the idea of being an asymptotic regime, okay? And what we see is that the simulation coming from the limiting Orsten-Uhlenbeck, non-Gaussian Orsten-Uhlenbeck are nicely fitting the shot noise, while the Orsten-Uhlenbeck is far off. We are able actually to compute the quantity of interest of particularly the Levy measure, the mean and the second moment of these processes as a function of the initial jump amplitudes and as a function, as a function of the intensity and as a function of the parameters of the jump amplitudes. Meaning that even if you do not want to run the limit because you are interested in a different type of approximation, you now have a way of replacing the shot noise for a finite but large value of lambda n with this type of non-Gaussian Orsten-Uhlenbeck processes, okay? Well, here is a bit more of what I was saying. Let me just conclude with one final remark. There is actually a way of getting an Orsten-Uhlenbeck as a limiting process, and it's kind of cheating. So right now we are having jump amplitudes that were only positive. So we were imagined to have jump amplitudes that are positive with probability 1 minus Fn and negative with probability Fn. Right now we were saying, well, Fn is equal to 0, so we have jumps that are positive with probability 1. Now imagine to allow for having negative jumps with probability Fn, and Fn goes to infinity. Well, you can trick it a bit, you can play around, and we were able to show that you can find some positive and negative jump amplitudes such that all these 4 conditions that are those yielding a diffusion limit are met. So by allowing the possibility of having negative jumps happening with a frequency with probability going to 0, you're able to recover the Orsten-Uhlenbeck process. And the trick behind is that you can show that allowing that corresponds to having a sort of generalized time model, which has been shown by Petri and others, that in the case where these jumps are actually constant, it has an Orsten-Uhlenbeck process. So that's the way of cheating by saying, well, Jn is not anymore a positive quantity, but is a real value. So that's why you get back to the Orsten-Uhlenbeck process. So as usual, I'm talking too much. I stop here. The paper has been published on Physica D. This is the reference for the code in case you're interested. And well, the main message, or one of the messages, is that we are coming from a different community. We have a different background. Maybe we should be careful when we talk about diffusion approximation, because Dev will have saved me a couple of months getting through the paper and say, no, that's totally wrong. That's totally wrong. That it doesn't make sense. And then realizing that it was a different idea, a different meaning, a different notion. And other than that, the selling message is that if you want to approximate the shot noise with something else, maybe instead of using the Gaussian Orsten-Uhlenbeck, you might use these non-Gaussian Orsten-Uhlenbeck processes, and some characterization of that are available in the paper. Thank you for listening.
Thank you, Massimiliano. I see a first comment from Cindy Greenwood. Cindy, please.
Thank you, Laura. I want to say that I also had the privilege of working with Piotr Lansky. I appreciate this talk very much. Masi, you did a great job.
Thank you, Cindy.
And I think I can see the hand of Piotr Lansky in this work. One thing that I very much appreciated in working with him is his way of looking again at something that has been many times passed over and finding something new and interesting. It's just amazing. Beautiful example of this. Thank you, Masi.
Thank you, Cindy.
I absolutely agree with Cindy. Let's say that this session can be partly dedicated to Peter, because here we have Ryota and Massimiliano, who were his collaborator for many years, as well as I was and you was. And I see there is Susan and many others that have long story with him, and we learned a lot from him, reading better all paper also. Are there other comments or questions?
Can I ask a question to Massimiliano?
Yes,
Yes,
sure.
please.
Please.
Can you show me slide number 7, Massimiliano?
Yeah. Yes.
There is the main theorem.
Yeah.
Yeah, okay. So this is 8. Go. The slide before.
Sorry, I was messing up with the, yes.
7. That is the point. So here you are saying that, okay, the random variables J, K are non-negative, true?
Mm-hmm. Yeah.
So it means that your limit process, capital L infinity, is always a subordinator.
Yes.
Okay. So, and what do you know what are conditions so that the Levy measure of the so in condition on J, so that the Levy measure of the limits subordinator is infinite?
Well, not really, in the sense that this happens. This happens for the gauche, for the gamma. So if the initial jumps are gamma, or
maybe not necessarily on the J con E, but on the limit, because the parameters also is relevant to get an infinite Levy measure.
I don't really know. Well, I mean, in the case of the only case where we do not get this is for the Bernoulli or the Poisson jumps, which has a kind of unit jumps, while in the other case, this was not true. But one possibility might be related to the behavior of the second infinitesimal moments.
Okay, but okay, suppose that
I'm sorry, they are asking to free the channel. I have to ask you to continue the discussion privately.
Okay.
I wanted to start the micro talks.
Okay, perfect.
Okay, it's okay.
Out of
We
time.
will speak
I'm
about this
very
later.
sorry. I have to thank everybody for participating, and clearly each one has addresses to write each other for further discussions. Thank you all. And
Thank you
we
very
are
much.
closing this section, thanking all the speakers. Bye.
Bye.
Thank you very
Bye-bye.
much. Thank you very much.
Thank you very much.
Surely anyone